The probability that a project will be completed in a certain amount of time is the joint probability that each of its paths will be completed within that same amount of time. That's the reason why, if you're analyzing the probability concerning a project's completion time, you don't necessarily need information about all its individual activities. You only need information about its paths. This problem is a good example of that situation because that's all that you're given. Let's take a look. Path ABE has a 55% probability of being completed within 3 weeks. Okay, I'm just going to take some notes here. Path ABE. What we're saying, a 55% probability, I'm just writing that in terms of decimal places. Okay, so there's a 55% chance you'll get done with that particular sequence in 3 weeks. Path CDF has a 90% probability of being completed within 3 weeks. Okay, that same amount of time. All right, I'm just making a note here. It said this, CDF, 90% probability in decimal places is 0.9. Okay, fine. If these are the only two paths within the project network, what is the probability that the project will take 3 weeks? Exactly that same amount of time. This problem is an invitation to practice the principle of joint probability. This project only has those two paths. So in order to calculate the likelihood the whole project will be done in 3 weeks, you have to calculate the joint probability that the two paths will be done in 3 weeks. What you have here is the individual probabilities of each one. Joint probability is super easy to calculate. You just multiply the paths together. Joint probability. You just multiply the probabilities together. Okay, so in your calculator you say 0.55 times 0.9. I get that's 0.495, or essentially, in probability speak, 49.5%. Yes, that's the answer to this particular question. Given those two paths and their two risks of being done within 3 weeks, then you have a 49.5% chance that the whole project that consists of these two paths will be done in 49 weeks, or 3 weeks, be done in 3 weeks. A 49.5% chance they'll be done in 3 weeks. The next question is really the same sort of question, but there's even fewer paths. A certain office building must be renovated and then sold. Okay, oh, all right. I'm sure that's going to be important. Renovation of similar buildings has taken an average of 4 weeks and a standard deviation of 1. Once placed on the market after renovations, building like this take an average of 10 weeks to sell and a standard deviation of 2 weeks. Assuming the renovation started now, what is the probability this office building would be completed? Now, that's kind of what's similar to last time. If you treat this as a project, it's asking about the risk. What's the probability of it being sold within 15 weeks? This problem, though, it kind of pays to diagram it if you don't see immediately what you need to do. What this is saying is we have a very small project. You just described it to us, right? This certain building that must be renovated and then sold. So if you were to draw a network, you know, it would have a starting node. There is this task, this activity of, you know, renovation. And then sale. And this project, like any project, would have a finish or an ending node. And really, the network structure of this project would look like that. It's the only logical structure for it. You must renovate it, and then when the renovation's done, you can sell it, and then when it's sold, the project's over. Oh, all right, so that actually, that's what the project network looks like. It's just that one straight line. Oh, it's just one path. Oh, it's just one path. So in order to comment on what's the probability that we'll actually get this building sold within 15 weeks, we need to gauge what is the probability that we would be done with this one path in 15 weeks. Okay. Well, we were given that detailed information about these two components of the path. Essentially, what did it say? Renovation of similar buildings has taken an average of I'm going to use mu for average, 4 weeks. We could also treat that as expected time. I was just a little too lazy to write expected time. But the average of 4 weeks and a standard deviation, sigma is much easier to write, of 1 week. Whereas here, once placed on the market, buildings like this one take an average of, you could write expected time, I'm just going to write mu, 10 weeks, and a standard deviation of 2. All right. Now, if this task has an expected time of 4 weeks and this task has an expected time of 10 weeks, then we already know the expected length of this path, because the expected length of path would just be the 4 plus the 10, or 14 weeks. Oh. Well, yeah, actually, that's logic. You think on average the renovation is going to take 4 weeks and then it's going to take another 10 weeks on the market to sell. Then you expect that this whole thing on average is going to take about 14 weeks. It's the expected length of the path. Because there's only this one path, that is also the expected completion time of the project. Now, the question wasn't asking about 14 weeks, it was asking about 15 weeks. We're saying that we expect it's going to take about 14 weeks, and the question's asking, okay, fine, well, what is the chance then that it'll be done within 15 weeks? In order to answer that, we don't need to know simply the expected length of the path. We need to know its standard deviation. And so we have standard deviation. It said standard deviation of 1 and standard deviation of 2. Those are the standard deviation in the component activities. We need the standard deviation in the path. Well, then you just say the 1 plus the 2, right? Never do that. You cannot add standard deviations. You cannot add standard deviations, you can only add variances. Technically, what we will pursue is the variance in the path. The path variance. Okay, all right, well, how do you find the variance in the path? You add the variances along the path. You can add variances. You say, well, we weren't given variances. But variances are easy. The variance in something is the square of its standard deviation. That's why variance is written sigma squared. So in the case of renovation, since the standard deviation was 1, the variance is also 1. In the case of sale, the standard deviation was 2, so the variance is 4. Oh, so the variance in the path, you can add up variances, would be 1, that 1, plus 4. It has a variance of 5 weeks. It has a variance of 5 weeks, which means it has a standard deviation of take the square root of 5. You say, well, yeah, okay, why would I want to take the square root of 5? Because we're still trying to figure out what's the probability that this will all be done in 15 weeks. In order to do that, we need to calculate a z-score. We need to calculate a z-score. Now, wait a minute, a z-score or a z-value? Right, that's that business about the z-score is the number I'm interested in minus the expected divided by the standard deviation. I'm talking about for this path, so I'm talking about this information right here. I need to fill out that ratio. Okay. Well, first off, x the number I'm interested in. What number is it that I'm interested in? Oh, yeah, back to the original problem, 15. We were worried about this when we're going to be done within 15 weeks. That's the number that we're essentially evaluating. Okay? The expected length, we're talking about the path, 14. The standard deviation in the path, right. That's where we do need to remember that then you take the square root. But, okay, 15 minus 14 divided by the square root of 5. Put that in my calculator, I get 0.45. So, okay. Is that the answer? No, that's a tool. It's a tool, a means to find the answer, because we take that 0.45 to the z-table. Oh, the z-table. Why did we calculate that z-value? Because we wanted to translate our particular path's distribution. You know, it's got a center of 14 and it's got this variance of 5. We wanted to translate it into a standard normal curve, something that has a center of 0 and a variance of 1. Why? Because we have this nifty table always at the back of just about every business textbook there ever was that tells us if you look up that translation, that z-score, what the area is. What the area is to the left in this particular case, because that's going to correspond to, on our table, if a 15 was here, a 14 was here, you know, and the variance was 5, it would tell us how much of the curve was to the left of the 15, which would tell us the chance that we would actually get done. Oh, but that means that we have to look up that number, 0.45. Right, a z-table. On a z-table, the first two numbers you're given tell you the row. The third number you're given, 0.05, to add up to 0.45, gives you the column. I'm trying to find the actual point in the table that applies to us. It's right there. And it says 0.6736. What does that mean? It means that if you chopped the normal curve that represents our path that's centered on 14 and has a variance of 5, if you chopped it at 15, this much of the curve is to the left of that. Oh, okay. And so that means, well, that means that there is that much of a chance of getting done within 15 weeks. 0.6736, yeah, that's the answer to this problem right here. It's that 0.6736 that came out of the table. Or another way to think about it is essentially 67%. This particular project in which you renovate a building and then you put it on sale, what is the chance that you're actually going to successfully have sold it within 15 weeks? About 67%.